Hello students, I'm here to start you on week 16's Desmos. So screen 1 is an engaged question with 4 questions. You don't want to spend any more than just 5 minutes max answering these questions. So you should be able to look at log base 10 of 10 and evaluate it. What is that equal to? So you're going to do that for each of those 4 questions. Then you're going to move on to screen 2, where you see the essential question: why do we use E in exponential models? So you may not know what E is yet, but that's okay. We're going to talk about it today. You do know what exponential models are and what they look like. So keep that in mind and think about how does the number E affect it. From there, you will move on to screen 3. So screen 3 and 4, both of these are the explore. So you're going to do a little bit of back and forth. So on screen 3, it says to solve the equation 10 to the power of m is equal to 19. Tyler writes the equation in logarithmic form. M is equal to log base 10 of 19. He then presses log on his calculator, enters the number 19, and writes down the approximation 1.279. Priya, a different student, follows the same steps and writes down 1.27875. So you're going to try the same thing on your calculator, write down what you get, and then answer this question here. Then on screen 4, it says to express the solution to each equation using a logarithm. Next, find the approximate value of a solution using a calculator. So you're given the exponential equation, write it using a logarithm, and then find an approximate answer, and so on. So that is the engage and explore. You're going to want to do those on your own before you get to screen 5, the guided instruction. So make sure screens 1 through 4 are done before you get to screen 5. And screen 5 is guided instruction. So it says these equations express the same relationship between 2, 6, and 14. We're told log base 2 of 16 equals 4, and 2 to the power of 4 is equal to 16. So I'm going to actually show you this picture really quick. And we're shown an exponential equation and a logarithmic equation. So both of these two are equal to each other. They are the same thing written in different ways, either exponentially or logarithmically. They both include a base. They both include an exponent to raise that base to, and they both give the value x. So we're going to keep this in mind as we are completing these problems on this screen here. So for example, log base 2 of 16 is equal to 4. That's the logarithmic expression. And 2 to the power of 4 is equal to 2. That is the exponential expression. What they're saying is that 2 is the base, 4 is the exponent that we can raise the base to get 16. Okay? So this is just review. This is what we talked about week 14, the week before Thanksgiving break. So we're going to now take that knowledge, that information, and if we're given the exponential form, we're going to write it as logarithmic. And if we're given the logarithmic form, we're going to write it in the exponential form. Okay? So for A, row A, we're told that 2 to the power of 1 is equal to 2. So if it's going to be written in the logarithmic form, we need the word log. We need the base 2. in this example, the base is 2. In order to get 2, we would have to raise the base 2 to the power of 1. For row B, we're told that base 10 can be raised to the power of 0 to get 1. So I would write my log base 10 of 1 is equal to 0. I can take 10, raise it to the power of 0, and get 1. So then for row C, I'm actually given the logarithmic form. I want to write it in exponential form. So I'm told log base 3, so here's my base, of 81, so it's going to equal 81, is equal to 4. So I can raise 3 to the power of 4 to get 81. For D, I'm told log base 5 to raise to the power of 0 is equal to 1. For E, I'm given the exponential form 10 to the power of negative 1 is equal to 1 over 10. So if I want to write the logarithmic form, I have to write log. What's the base? The base is 10. I'd have to raise it, I want it to equal 1/10 by raising 10 to the power of negative 1. For F, I'm given the exponential form. I want it in logarithmic form, so I'm writing log base 9. I want it to equal 3, so I'm going to raise 9 to the power of 1/2. For G, I'm given the logarithmic form. I'm told log base 2 is going to equal 1/8 if I raise 2 to the power of negative 3. So 2 to the power of negative 3 is equal to 1/8. For H, I'm given the exponential form, and I want it in the logarithmic form. So I'm going to write log. What's my base? My base is 2. I want it to equal 15. So I'm going to raise 2 to the power of y. For row I, I'm given that. Log base 5, I want it to equal 40 by raising it to the power of y. And then for row G, I have my base B. I want it to equal x by raising it to the power y.
All right, so a really important concept in mathematics is something called E. Now, before you get confused on what E represents a number. So E is just a number. It's just a number. It's about 2.718. It's an irrational number. So it means you can't write it as a fraction. You can't write it as a decimal that terminates or repeats. So like, 2/3 is an example of a fraction that can be written as a decimal that goes on forever, but it never stops, right? It's just repeating sixes forever. Or 1/4 is an example of a rational number because it can be written as decimal 0.25 with zeros repeating forever, right? So those are rational numbers. E is irrational. So I want to compare that to like pi. Pi is an irrational number. It starts off 3.1415926 and so on. So E is just like that. So it's 2.718 and it keeps on going. Okay, so it's got a lot of decimal places, infinitely many decimal places. It's called E because it's named after a guy named Euler. So Euler. His name was Leonhard Euler. So that's how you pronounce that. He lived in the 18th century. He's one of the greatest mathematicians to ever live. And all you need to keep in mind is that E is used a lot to represent things in nature. So when things are showing up in nature, that we use E to represent them. All right, now below it says select all that are true. I want you to take what we just talked about. You can reread the paragraphs above and select which statements are true. As soon as you're done, you can move on to the next slide. All right, now we're going to get a little bit of a chance to practice using E on the calculator. So E is actually on a calculator, and we can use it to calculate things. So today we learned that E is just a mathematical constant who is approximately 2.718. When we work with problems with E, we always use the calculator. And the reason why we always use the calculator is because there's no good way to multiply a number that goes on forever, right? So we want to use a calculator because it's going to have a lot more decimal places that we can use. So the first thing I want you to do is I want you to pull up a calculator. If you have one at home, that's cool. If you need to pull one up on the internet, that's great too. My recommendation is the Desmos Scientific Calculator, and it's linked in Google Classroom with this assignment. So go ahead and open that up, the Desmos Scientific Calculator. And I want you to find the E button on your calculator, and I just want you to experiment with how it works. So see if you can do 2 times E or E squared. See if you can calculate a few of those. So pause the video, play around with the calculator real quick, use E on the calculator, and see how it works. All right, for part 2, what we're going to do is we're actually going to try a few of these on the calculator, and I've given you the answer for all of these about what you should get on the calculator. So our practice right now is, can you use E on the calculator correctly? Okay, so the first one I want you to find is 10 times E raised to the 1.1 power. Now, if you do this correctly, you should get 30.04166. Okay, so I want you to go over to the calculator and type in those 3 expressions, and then you should get the same answer that I did. If you don't get the same answer that I did, you should try it again until you do get it. Once you've gotten it, I want you to come back to the Desmos, and I want you to check them off so we can see which ones you got. So maybe you only got these 2 and you weren't able to figure out how to type in the second one. If that's the case, then we'll know and we can go over it a little bit more in class. So check the ones that you were able to correctly calculate on your calculator, and then move on to the next slide. All right, so let's just think real quick about this exponential function, e to the x equals y. Now, if I wanted to put this in logarithmic form, the way that I would do that is exactly the same as I would with any other exponential function. So thinking back to what Miss Woodard showed you a few slides ago, this is what we would get. We would get log base e of y equals x. So our base in this case is e, the number 2.718, and so on. So we have 2 equivalent forms. But here's the thing. Remember I said that e is such a special number, right? It has its own name, right? It's like pi. It got its own symbol. So it's so special that it actually has a special name for its log, and it is called the natural log. So it's called the natural log, and instead of writing everything like this, log base e of y, we actually have a special button on our calculator just for log base e, and it looks like this. ln of y equals x. So this and this mean the same thing. If you see ln of something, that means log base e. ln stands for logarithmic natural, right? So, in Spanish sometimes, or in Latin or French, it's the words are opposite of the order that we would use in English. So if I wanted to say blue pants, in Spanish, I would say pantalones azul, right? So I'm flipping the name and the color. Same thing here. Instead of natural log, it's log natural. So that's what ln stands for. And so it's the ln of y equals x. So that is related, or is the same thing as log base e. So instead of writing log base e, you can just write ln. And we all know what you're talking about. You're talking about log base e. Here's another special one. So our numbers are all base 10. So every time we get to a 10, we go to another place value in our numbers. And so 10 is a really important number in our mathematics. So this one also is special. So 10 to the x power equals y can be written as log base 10 of y equals x. And so our calculator can do this one as well. And the way that it's written is just whenever you see log without a base on it, if there's no base written, it's missing one, we just know that that means that it's 10. It's just like when we have an exponent of 1, we can just write that without the exponent. Or if we have 2.0, we can write that without the decimal, right? So it's one of those things that we just leave off because we use it so often, right? And so it's kind of like our invisible base. Whenever there's the base missing, just assume it's 10. All right, so this is what an equation looks like often when we're using E. So this is not always, but it often looks like this. So it sometimes can look a little bit different, but this is one of our formulas when working with E. And so when we're using E, if this looks like an exponential function because it is an exponential model. So I want to remind you all that when we're working with exponential functions, they often look like this. They look like a times b to the x power, where a is our starting point, b is our growth factor, x is our interval of time that we're evaluating over. With E, it has this same kind of setup where you have a number times E raised to a power. Okay, so let's break down what these things are. So P of t right here, this represents our output. So this is what we get when we evaluate our function. So, oftentimes this looks like we use E a lot when we're talking about banking, if we're talking about interest rates. So this might represent your principal plus interest, or it might represent the population size of something, right? So that's what the P of t represents, an output. T over here, this is our input value. This is what we plug in. And a lot of times this is time, right? So most functions are a function of time. And so we're often putting in how many days, how many months, how many weeks, how many years. That's minutes, hours. That's what we're plugging in a lot of times when we talk about t. All right, so what is this 13? Well, that's the value when the function when t is something. When t, remember this list is in the spot of our a, so this is actually when we're starting, right? This is when t is 0. So when time equals 0, our population is 13, or our principal amount of money we put into our interest account is $13 or something. That's our starting place, right? 13 is the starting amount. What is the constant E? Well, E is just a number, right? It's just approximately 2.718. It's some number right around there, okay? So that's what E is. And then this new thing that we have in our equation as well is this 0.045. And so E is the growth factor, and 0.045 is the continuous growth rate. So we can also say that it's about 4.5%, but the decimal is used in the number, not of the function. So we don't use percentages in our functions, we use decimals. Okay, so this is how we can identify things. So this is our starting place, this is our growth factor, this is our continuous growth rate, and this is our input value. Okay, so those are the parts of a exponential function with E in it. All right, so let's go ahead and answer some questions. Let's see if we can identify these different parts of an equation on the next part. Okay, so on these next three problems, sometimes they give you the function, sometimes they don't. And it's our job to either write the function or identify some part of the function. So let's read the first one. At time t equals 0, measured in hours, so they just told us that it's in hours, a scientist puts 50 bacteria in a gel on a dish. Okay, the bacteria are growing and the population is expected to show exponential growth. So the population of the bacteria is our output. How many bacteria are there after so many hours? Our input is hours for t. And then we have 50 times e raised to the 0.25t. So if we are going to identify our continuous growth rate per hour, all we have to do is look at where in the function is continuous growth rate represented. And that's represented what you're multiplying your t by in your exponent. So our continuous growth rate is 0.25. Okay, that's the spot that it goes in our function. Okay, so 0.25 is our continuous growth rate per hour. Okay, so that is, we looked at the function and we just found what the continuous growth rate was. All right, that's all they wanted for that first one. Okay, and number 2, in 1964, the population of the United States was growing at a rate of 1.4% annually. That year, the population was approximately 192 million. The model predicts the population in millions T years after 1964. So they identified the continuous growth rate for us per year as 1.4%. Now we need to turn that into a decimal. So that is equal to the decimal 0.1% is going to be 0.1 like this. And so 1.4% is 0.014. Okay, so that is our continuous growth rate. And now if I want to write a function for this, I just need to know a couple of things. What's my starting population and what's my continuous growth rate? And I can write it. So we started with 192 million people times E, and we're raising E to the 0.014 times T. And that's it. There's our function. Okay, 192 times e raised to the 0.014 t. So we have identified the function for number 2. All right, and then for number 3, we're going to go ahead and skip that one, so you can just mark that one off. We don't have time today to talk about it.
So now we are on screen 9 of week 16. This is the guided instruction for 13.4. We're given a graph to model the function defined by p of t is equal to 50 times e to the power of 0.014 t. So we have this function here modeled on the graph here. A says the equation models the population in millions in the US T years after 1964. What does the model predict for the population of the US in 1974? So I'm going to point out that this is just a model predicting or estimating what the population will be at different years after 1964. So our x-axis is telling us years since 1964. Our y-axis is telling us the population, or an estimate of the population. So 1974 is 10 years after 1964, and the model predicts. So I'm going to look at my graph. I'm looking for 10 years after 1964. I want to know what y value does the graph give me 10 years after. That looks like to be about 220 million. So according to this exponential model, in 1974, 10 years after 1964, the model, I'll say the exponential model, predicts the US population will be 220 million. So I got that just by looking at the graph. Part B says, in which year does the model predict the population will reach 300 million? So now they're telling me the population P of t will equal, the function P of t will equal 300 million. What t value will give us 300 million? So I want to see at what point does the graph have a y value of 300 million? What x value does that coordinate with? And that coordinates with, 32 years after 1964. So 1964 plus 32. This is the year 1996. So part B, in which year does the model predict the population will reach 300 million? The model predicts the U.S. population will be 300 million in the year 1996. So from there, you scroll down. I have to switch screens, but you scroll down and you see the next question. Research what the population was in the U.S. In the year the model predicted 300 million. So in 1996. So remember that this function and this graph, they are just predictions. So they had created this exponential model in 1964, and they used it to make an estimate of what the U.S. population will be t years after 1964. So now we're actually going to look at what the U.S. population actually was in the year 1964, and I Googled it already. It was 269.7 million. How far off was the model? So the model was 30.3 million people off. So the exponential equation that they came up with in 1964 wasn't super accurate for the year 1996. What factors do you think, so I'm reading the next question, what factors do you think account for the actual population in that year being different from the prediction of the model? And the answer is, there's so many different things that can affect a population size. Immigration can... So there's immigration, right? That's people who come into the country and live in the country. So if for a few years, there's a bunch of immigration in or a bunch of, I think the word is emigration out, that can affect the population size. The amount of births compared to the amount of deaths can also affect the population size. So for example, if there's more deaths for a while because of a war, for example, Vietnam War, that could affect the population size. The economy can also affect the population size because if, let's say, the economy is not doing super well, so people are probably going to be choosing to not have kids, so the births might go down. There's all sorts of different factors that can affect a population size. So we can write some of these down. So the last question is, in what year did the U.S. population actually reach 300 million? And that was actually in 2006. So I had Googled that earlier. You can always double check. But the U.S. population reached 300 million in the year 2006. So turns out that was about 10 years later than what that exponential model originally predicted. So that's 10 years later. And the reason why is because of all those different factors that we just talked about. So when they created this exponential model, this one right here, in 1964, they based that model off of things happening in 1964. The factors that were in play in 1964, the economy, the wars, all of that in 1964. But those factors can change over time, like we just talked about. So that those different factors, those changes in factors, changes in times, they may be more relevant, they may be less relevant. So this exponential function is more accurate, closer to 1964. As we get further away, it's going to be less accurate. And that's it for today. So make sure you take all the notes that you need to, so you're prepared for class on Tuesday or Wednesday.